Welcome to the first lecture. This video serves as introduction to the first lecture. Now let us look at the term Model Predictive Control, which is also known as MPC. In short, we can divide this term into two meaningful parts. First is model. Now what does this signify? As the word says, the model of the process is used in this MPC algorithm. And usually a model of the process is a mathematical representation of its behavior. And to represent its behavior in a mathematical form, we can do so in many different ways, which means that the behavior of the model can be represented by many different kinds of models. Not all kinds of models are very useful for this course, especially for the MPC algorithm. We will later on talk about what kind of models are well suited for model predictive control. The second meaningful part is this term predictive control, or in other words, control algorithm that uses prediction. But what kind of prediction? MPC is an algorithm which utilizes the predicted future behavior of the process. For example, let's draw a time axis. Let's assume that you are at a time which corresponds to, say, for example, 3 seconds. And this is your current time. For MPC algorithm, we predict how the plant or a process will behave in the future from the current time. For example, we predict how the plant will behave between time equals to 3 seconds to time equals to 8 seconds. And then we use this time axis to predict equals to 8 seconds. And then we use this information. Now the question is, from the current time, how can we predict the future behavior of a plant in a real plant? We cannot make it run into the future, can we? That would be ridiculous to do so. So if a real plant cannot be made to run into the future, how do we do so? Here is where the model of the process helps us. Since the model of the process is mathematical representation of the behavior of the process, we use its model to predict its future behavior from the current time. And we can do so because we can simulate a mathematical model from a given time to any given time in the future as long as we know its state at the current time. How long into the future should we predict the plant behavior? In this example, it was between 3 seconds to 8 seconds, knowing its current position or current state at 3 seconds. The length of this future horizon is called the prediction horizon. And the prediction horizon is a parameter in MPC algorithm that can be chosen by the user. Alright, until now we know that the model of the process is used to predict its behavior into the future, but still the question is, okay, so what do we do about this predicted future behavior? How do we use it? In MPC algorithm, the predicted plant behavior is utilized to formulate an optimal control problem. And when we talk about optimal control problem, it is in general an optimization problem. And such optimal control problems can be, for example, a setpoint tracking problem. For example, you want the output of a process to follow a certain set point. That can be posed as an example of an optimal control problem. Then this optimal control problem, which was formulated by utilizing the predicted behavior of the plant by using the model, has to be solved. The optimal control problem can be solved, and the best or the optimal values of the inputs that fulfill your control problem's objective will be used. We use the first value of the optimal control solution and then move one time step forward. So we use the first value, and from t equals to 3 seconds to t equals to 3 plus delta t seconds, where delta t is the sampling time, we move one step forward. And when we are now at this new time step, we will repeat the same thing. From this new position or new time, we will again use the model of the process, predict the plant behavior, formulate an optimal control problem, solve the optimal control problem, and then use only the first optimal control value. And then we repeat this process again and again until we reach to the end of our simulation time. Well, that was the main concept. Let's not jump into the details of how this algorithm works. We will first start by looking into the first part, which is the first meaningful term, the model. There are different types of models that are suitable to be used with MPC problems. For example, state space models are very much suitable to be used with MPC. Also, input-output models are very well suited to be used with MPC problems. In practice, MPC is implemented in computer or a microcontroller, which are digital devices. So let's first start with discrete-time models. Again, in discrete-time model, let us start with discrete-time state space model. The discrete-time state space model can be both linear and nonlinear. The nonlinear discrete-time state space model is written as follows. The first equation is the state equation, where f is any nonlinear function of time. The state and the control imputes. The subscripts k is the discrete time, x is the state. This equation is the measurement equation, where g is any nonlinear function of time. State and the control imputes. The model can have more than one imputes, more than one states, and more than one outputs. X can be from x1, x2, all the way up to x of n. So in this example, we have assumed that there are n number of states, and this we write it as follows. Similarly, there can be more than one imputes, for example, u could be from u1, u2 to our number of u's, and this we write it as, and similarly the output can also be more than one, for example, m number of outputs. Similarly, the linear discrete time state space model can be written as follows. The first equation is the state equation, and the second equation is the measurement equation. X are the states, U are the control imputes. Here Vk and Wk are random process noises and the measurement noises. These random noises have zero mean and a certain variance. However, these two noises, the process noise and the measurement noises, are uncorrelated to each other, which basically means that the random process noise has got nothing to do with the measurement noise. AD, BD, CD, and DD are the system matrices, and the subscript D represents that it is a discrete-time linear model. Here also, the states, the imputes, and the outputs can be more than one. So, depending on the number of imputes, states, and outputs, the size of the system matrices AD, BD, CD, and DD are fixed. Taking this as an example, the size of AD will be a square matrix with a size that is equal to the number of states. Similarly, the size of BD can be written as, and for the remaining two system matrices, we can write their sizes as well. The sizes of these random process and measurement noises are as follows. Instead of using n, r, and m for denoting the number of states, control imputes, and for simplicity and for easiness, we can use a simplified symbol or a simplified notation. Here nx will represent the number of states, nu will represent the number of imputes, and New York will represent the number of outputs. So this is the notations that I will be following for this course. Now that we have looked into the discrete time state space model, let us also look into input, output, or polynomial models. They are also discrete time models. The polynomial models can also be both linear as well as nonlinear. The polynomial model can be expressed as follows. As you can see, in an input-output model or a polynomial model, the output depends on the previous outputs and the previous inputs. Here the current output is dependent on 1, 2, my number of previous outputs and mu number of previous inputs. And the relationship between previous inputs and previous outputs can be any nonlinear function, which is denoted by h here. Important thing is that in a polynomial model, the current output is only dependent on past outputs and past inputs. Here there are no states. So in polynomial models, we do not talk about states. The linear polynomial models can be of different forms. Let's have a look at them. It can be an ARX model, where ARX means autoregressive exogenous. Another type is infinite impulse response model and finite step response models. In this course, we will not be focusing so much on the polynomials models. So we will not go into details of these different types of linear polynomial models. Although I would like to show you one example of how an ARX model looks like. So here also we can see that an ARX model, current output depends on past outputs, mi of them, and the past inputs, mu number of past inputs. A1, A2, AMI are coefficient of these past outputs, and similarly B1 to mu are the coefficients of these past inputs. This ARX model can be represented in a more compact form for easier representation. Let's see how we can do that. We define a delay operator q, and this q is used in such a way that to represent yk1, we will use the delay operator q to the power -1 because it is past output but one time step before. So -1 and yk. Similarly for the past output which was 2 sample before with 2 sample delay, we will write q2 and yk. So this q is a delay operator because this k2 was 2 samples before yk. So yk has been delayed by 2 samples. Similarly for the inputs, we can also write using the delay operator to represent uk1 which is the input that was one time step before uk. We use the delay operator one time step before uk. To represent uk2, we will write using a delay operator k2 is 2 sample delay of uk and so on we will write for all of the terms that arise here in this ARX model. Now using this delay operator, we can rearrange this one in a more compact form. Let us do so. So this will become instead of yk1, we can use this term. Instead of yk2, we can use this term and so on for this one also. Similarly we will also express the past inputs using the delay operator. If we rearrange these terms, then we will get the compact form. Now, let us take yk common from this left-hand side expression and similarly let us take uk, and uk common from this right-hand side expression. Then we will have where this expression aq and bq can be written as follows. These actually are the coefficients that are present on each ytron in this left-hand side. These are the coefficients because yk comes common and these are the coefficients of each uk's that are present in the right-hand side. So this is a more compact form of the ARX model. Thanks for watching. If you enjoyed this video, please give it a thumbs up, subscribe for more content, and hit the notification bell so you never miss an update. See you in the next one.